Understanding the OSI and TCP models. The OSI Open Systems Interconnection and TCP Transmission Control Protocol models are a conceptual framework used to understand network interactions in 7 distinct layers. Each layer has a specific role, ensuring smooth data transfer and communication over a network. 1. Physical layer. The network's foundation builder. Function handles the physical components like cables, coaxial, fiber optic, switches, and hubs. It's focused on transmitting raw data bits across these hardware elements. Protocols includes Ethernet for wired setups and IE 802.11 for wireless. Analogy: think of it as the muscles and bones of the network, dealing with tangible aspects like voltage levels and physical connections. 2. Data link layer. The local network organizer. Function acts as a bridge between hardware and network functions. It organizes data into frames and manages error detection, correction, and data addressing using MAC addresses. Protocols, Ethernet, PPP, and ARP are key here. Analogy: a meticulous organizer ensuring data is neatly packaged and accurately delivered within the local network. 3. Network layer. The global data navigator. Function functions as the network's GPS, determining the best routes for data packets using IP addresses. It guides data across various networks. Protocols, IP, ICMP, OSIF, and BGP are essential tools. Analogy: responsible for smartly forwarding data packets along the most efficient paths. 4. Transport layer. The quality assurance expert. Function ensures complete and reliable communication across the network. Manages data flow, focusing on reliability and speed. Protocols, TCP for reliability and UDP for speed. Ports like HTTP 80, HTTPS 443, and FTP 2021 are significant. Analogy: oversees that the right data reaches the right application, maintaining quality in data transfer. 5. Session layer. The network's conversation facilitator. Function manages communication sessions between applications, much like a moderator in a discussion. Protocols, NetBIOS and PPTP, focusing on establishing and maintaining connections. Analogy: ensures smooth dialogue flow, controlling the timing and duration of interactions. 6. Presentation layer. The universal data translator. Function converts data into various formats, handling encryption and decryption for secure communication. Protocols, SSL and TLS, focusing on data representation and security. Analogy: the Rosetta Stone of the network, ensuring data is in the right format and secure. 7. Application layer. The user's digital interface. Function: the interface where users and network services interact. It's the front end of networking. Protocols, HTTP, FTP, and DNS, with significant ports like 80 HTTP and 443 HTTPS. Analogy: handles user-facing services like web browsing and email, providing the interface for network interaction. Exploring the TCP model. The TCP model is a fundamental framework used to understand how different network protocols interact in the Internet Protocol Suite. It consists of 4 layers, each with a specific role in handling network communications. 1. Link layer. The network's foundation. Function: this layer is responsible for the physical transmission of data over the network. It includes elements like Ethernet cables, switches, and network interface cards NICs. Protocols and components, Ethernet, Wi-Fi, and other physical network technologies. Analogy: think of it as the physical infrastructure or the road upon which all network traffic travels. 2. Internet layer. The global data router. Function: this layer handles the routing of data packets across networks. It determines the path data takes from the source to the destination using IP addresses. Protocols, IP Internet Protocol is the key player here, along with ICMP and ARP. Analogy: acts like a global positioning system GPS for network traffic, guiding data packets to their destinations. 3. Transport layer, the reliable delivery manager. Function ensures that data is transferred reliably and in the correct sequence. It's responsible for error checking and flow control. Protocols: TCP Transmission Control Protocol for reliable communication and UDP User Datagram Protocol for faster, connectionless communication. Analogy: comparable to a postal service that ensures your letters data packets are delivered accurately and in order. 4. Application layer, the user interaction facilitator. Function: this is where users interact with network services. It encompasses protocols that provide specific functionalities like web browsing, email, and file transfers. Protocols: HTTP, HTTPS, FTP, DNS, and SMTP are some of the key protocols in this layer. Analogy: think of it as the user interface of the Internet, where users access and use various network services and applications. Each layer in the TCP model plays a vital role in the smooth operation of Internet communications, ensuring data is transmitted efficiently and reliably across networks. While the TCP model is broadly used in real-world applications, particularly in the Internet, it's less granular than the OSI model, but provides a practical framework for understanding network communication, comparison, and practical usage. While both models aim to clarify network operations and assist in troubleshooting and designing networks, they are used differently in the field. The OSI model, with its detailed layering, is often used as a reference tool to understand network functions and design principles. Its comprehensive approach is beneficial for education, troubleshooting, and understanding the full scope of network operations. The TCP model, on the other hand, is more practical and aligned with the protocols used in the Internet today. It's widely adopted in real-world networking and is essential for understanding the Internet's operational framework. Importance in network design and troubleshooting. Understanding both models is crucial for network engineers. They provide a structured approach to diagnosing and resolving network issues and a language for describing network functioning in a layered manner. For troubleshooting, network professionals can identify at which layer a problem is occurring, allowing for targeted interventions. In network design, these models help in segmenting and organizing network architecture, ensuring each layer's protocols and components are optimized for efficiency, reliability, and security. In summary, while the OSI model offers a theoretical and comprehensive approach, the TCP model provides a practical framework aligned with the current Internet standard. Both are invaluable in the field of network engineering for efficient network design, management, and problem resolution. Understanding how data flows through these layers and the role of each ensures robust, efficient, and secure network operations. Network engineer training. Both the OSI and TCP models can be likened to the postal system in terms of how they organize and manage data transfer across networks. Here's how the layers of each model relate to the various aspects of the postal system. OSI model similarities with postal system. Physical layer OSI postal transportation. This is akin to the physical means of transporting letters and parcels, such as trucks, planes, and delivery personnel. It represents the physical infrastructure used to transmit raw data bits. Data link layer OSI packaging and addressing. Similar to packaging a letter and labeling it with a recipient's address, the data link layer takes care of framing data and providing physical addresses MAC addresses to the frames for delivery on the same local network. Network layer OSI routing. This layer functions as the postal sorting facility where letters are sorted and directed towards their final destination. The network layer determines the best logical path for data to travel across different networks. Transport layer OSI delivery assurance, comparable to registered mail services, ensuring the letter reaches the correct recipient and in the right order. The transport layer manages the reliability, flow control, and error checking of data packets. Session layer OSI organization of conversations. This is like managing a series of correspondence between two parties, ensuring that the conversation is organized and coherent. The session layer establishes, manages, and terminates the connections. Presentation layer OSI letter translation and encryption. Just as a letter might be translated from one language to another or sealed for privacy, the presentation layer handles data translation, encryption, and decryption. Application layer OSI postal services. This layer represents the postal services offered, such as mail sending and receiving. The application layer provides network services directly to the users. TCP model similarities with postal system. Link layer TCP postal transportation. This layer is analogous to the combination of physical transportation and initial handling of mail, similar to the OSI's physical and part of the data link layer. Internet layer TCP routing. Like the sorting and routing of mail based on destination addresses, the Internet layer routes data packets across multiple networks using IP addresses. Transport layer TCP delivery assurance, ensuring that messages are delivered reliably and in sequence. The transport layer in TCP is much like ensuring that mail is delivered accurately and intact. Application layer TCP postal services. This layer is where users interact with network services, akin to utilizing various postal services like sending letters, parcels, or registered mail. Similarities in functionality. Layered approach. Both models use a layered approach to manage and facilitate data communication, much like how the postal system uses a structured process to handle mail from sender to receiver. Encapsulation and decapsulation. Just as a letter is wrapped encapsulated and unwrapped decapsulated as it moves from sender to recipient, data packets are similarly encapsulated and decapsulated as they travel through the layers. Addressing and routing. Both models employ specific addressing schemes and routing protocols to direct data to its destination, akin to how the postal system uses addresses and sorting to ensure mail delivery. By understanding these similarities, network engineers can better grasp the complexities of data transmission and the structured process of communication within networks, leading to more effective design, troubleshooting, and management of network systems. Each layer's role and operation in the OSI and TCP models contribute to the overall efficiency and reliability of data transfer, much like the various components of the postal system work together to ensure the accurate and timely delivery of mail. View of network protocols and their ports. This guide offers an explanation of each network protocol alongside its associated port numbers, formatted for clarity and ease of understanding. FTP File Transport Protocol. Ports 2021. Description: FTP is used for transferring files between computers on a network. Port 20 is designated for data transfer, while port 21 is used for control sending commands and responses. SSH Secure Shell. Port 22. Description: SSH provides a secure channel over an unsecured network. It's primarily used for secure remote login, command execution, and other secure network services. Telnet. Port 23. Description: Telnet is a protocol used for text-based communication with remote computers or servers, primarily in command line environments. SMTP Simple Mail Transport Protocol. Port 25. Description: SMTP is the standard protocol for sending emails across networks. It's used by mail servers to send outbound emails. DNS Domain Name System. Port 53. Description: DNS translates human-readable domain names like www.example.com into IP addresses, allowing browsers and other applications to access Internet resources. DHCP Dynamic Host Configuration Protocol. Ports 67, 68. Description: DHCP is used for automatically assigning IP addresses and other network configurations to devices on a network, simplifying the management of IP addresses. TFTP Trivial File Transport Protocol. Port 69. Description: TFTP is a simpler, less secure version of FTP. It's used for transferring files, often in scenarios where user authentication is not required. HTTP Hypertext Transfer Protocol. Port 80. Description: HTTP is the foundation of data communication for the World Wide Web. used for transmitting web pages and other web content. HTTPS Hypertext Transfer Protocol Secure. Port 443. Description: HTTPS is the secure version of HTTP used for encrypted communication over a computer network, primarily in web transactions. SSL VPN Secure Sockets Layer Virtual Private Network. Port 443. Description: SSL VPNs provide remote access VPN capabilities using the SSL protocol to secure connections and allow remote users to securely access network resources. POP3 Post Office Protocol version 3. Port 110. Description: POP3 is used by email clients to retrieve emails from a server, allowing users to download and manage their email locally. NTP Network Time Protocol. Port 123. Description: NTP is used to synchronize the clocks of computer systems over the network, ensuring consistent timekeeping across devices. IMAP4 Internet Message Access Protocol version 4. Port 143. Description: IMAP4 allows email clients to access and manage emails on a mail server, enabling users to view and organize their emails without downloading them. SNMP Simple Network Management Protocol. Port 161. Description: SNMP is used for managing, monitoring, and configuring network devices like routers and switches, as well as for collecting network performance information. IPsec Internet Protocol Security. Port 500. Description: IPsec is a suite of protocols used to secure Internet Protocol IP communications by authenticating and encrypting each IP data packet. RDP Remote Desktop Protocol. Port 389. Description: RDP allows a user to connect and interact with another computer over a network, providing remote access to the desktop and applications of the target machine. SMTP TLS Transport Layer Security. Port 587. Description: SMTP TLS enhances the security of SMTP by facilitating encrypted communication. This is used for secure email transmission over the network. LDAP over SSL LDAPs. Port 636. Description: LDAPs is the secure version of LDAP Lightweight Directory Access Protocol, using SSL to encrypt the communication. It's used for accessing and maintaining distributed directory information services securely. IMAP over SSL. Port 993. Description: this protocol is a secure version of IMAP, using SSL encryption to protect the transmission of email messages to and from a mail server. POP3 over SSL. Port 995. Description: POP3 over SSL provides a secure version of the POP3 protocol by incorporating SSL encryption for the secure retrieval of emails from a mail server. Microsoft SQL Server. Port 10433. Description: this port is used by Microsoft SQL Server, a relational database management system, for establishing connections to the database server. SQLNet. Port 10521. Description: SQLNet is used by Oracle SQL databases for network database access. This port facilitates communication for Oracle database clients and servers. MySQL. Port 3306. Description: this is the default port for the MySQL database system used for database management and access. SIP Session Initiation Protocol. Ports 5061 TCP, 5060 UDP. Description: SIP is used for initiating, maintaining, and terminating real-time sessions that include voice, video, and messaging applications. SMB Server Message Block. Port 445. Description: SMB is a network file sharing protocol that allows applications on a computer to read and write to files and request services from server programs in a computer network. Syslog Protocol. UDP. Description: the Syslog protocol is used for logging system messages in an IP network. It's widely used for system management and security auditing. SNMP Simple Network Management Protocol, Port 161 UDP. Description: SNMP, primarily using UDP, is utilized for monitoring, managing, and configuring network equipment, as well as for collecting network performance data. Each of these protocols plays a critical role in various network functions, ensuring smooth and secure communication and management across diverse network environments. Here's a succinct list of network protocols and their associated port numbers. Network protocols and their functions. DNS Domain Name System. Analogy: consider DNS as the Internet's phone book, translating website names like Google.com into their numerical IP addresses, much like a contacts list in your phone. DHCP Dynamic Host Configuration Protocol. Analogy: DHCP is like a maitre d' at a restaurant, assigning a unique IP address similar to a table number to each device as it connects to the network, ensuring smooth communication without conflicts. NTP Network Time Protocol. Analogy: NTP acts as a universal clock setter, synchronizing all network devices to the same time, essential for coordinated actions and maintaining security protocols. Types of DNS records. A record address record. Explanation: associates a domain name with its IPv4 address, similar to linking a person's name to their home address. A record quad a record. Explanation: functions like the record but maps domain names to IPv6 addresses, allowing for a greater number of unique addresses. See name record canonical name record. Explanation: works like a nickname, mapping an alias to the actual name of the host. It's useful for linking subdomains to the main domain. MX record mail exchange record. Explanation: serves as the email world's postal system, directing emails to the appropriate mail server. NS record name server record. Explanation: guides internet queries to the authoritative name servers for a domain, similar to a guide in the DNS system. PTR record pointer record. Explanation: used for reverse DNS lookups, converting an IP address back to a domain name, akin to a reverse phone book lookup. SOA record start of authority record. Explanation: contains crucial administrative details about the domain, like the primary name server and the domain administrator's contact info. TXT record text record. Explanation: holds various text-based information for different purposes, such as verifying domain ownership or implementing email security protocols. Explained the DHCP process. Understanding the DHCP Dynamic Host Configuration Protocol process can be made simpler and more relatable with the use of everyday analogies. Here's a breakdown of each step in the DHCP process. DHCP Discover. Analogy: this is like arriving at a party and asking if there's a seat available. In technical terms, your device broadcasts a message on the network seeking a DHCP server. DHCP Offer. Analogy: imagine the DHCP server as the party host, hearing your request and responding with an offer of a specific IP address. This is akin to being offered a specific seat at the party. DHCP Request. Analogy: after receiving the offer, you, the device, confirm your choice of the offered seat. This step involves your device sending a request back to the server to confirm the IP address it has been offered. DHCP Acknowledgement. Analogy: the server party host confirms that the seat IP address is officially yours. The DHCP server completes the process by sending an acknowledgement packet to your device, finalizing the IP address and other network settings like subnet mask, default gateway, and DNS servers. This analogy-driven explanation aims to provide a clear understanding of the DHCP process, making a technical concept more accessible and easier to grasp. GPT. Network Engineer Training. In the world of network engineering, understanding and orchestrating the symphony of network protocols and their functions is crucial for seamless digital communication. DNS, DHCP, various DNS records, and the DHCP process are core components that ensure efficient and secure data exchange across the network. DNS domain name system is akin to the Internet's phone book, translating user-friendly domain names into numerical IP addresses, much like a contacts list in your phone. It ensures users can access websites with easy-to-remember names, while the network translates these into IP addresses to locate and deliver the content. Meanwhile, DHCP Dynamic Host Configuration Protocol plays a critical role, similar to a maitre d' at a restaurant, assigning unique IP addresses to each device as they join the network, ensuring smooth communication without conflicts. This dynamic allocation of IP addresses is essential, especially in environments with a large number of connecting devices, maintaining order and efficiency. Understanding the types of DNS records is like knowing the various types of entries in a directory, each serving a unique purpose. A and IA records connect domain names to their respective IP4 and IP6 addresses, ensuring the right domain points to the right server. CNAME records allow for aliasing, making it easier to manage and redirect traffic within domains, while MX records direct email to the correct mail servers, ensuring that your emails reach their intended destination. The DHCP process, with its discover, offer, request, and acknowledgement steps, is a dance of negotiation and confirmation between devices and the network, ensuring each device is properly integrated into the network with the right settings for optimal communication. This process is crucial in maintaining a flexible yet orderly network environment, allowing for scalability and adaptability as devices come and go. Each of these components, from DNS to the DHCP process, plays a vital role in the network's operation. They work together to ensure that data is routed correctly, devices are recognized and can communicate effectively, and the network remains secure and efficient. For network engineers, mastering these protocols and processes is not just about technical knowledge, it's about ensuring the digital world remains connected and communicative, reflecting the ever-growing need for robust and reliable digital communication in today's interconnected world. Understanding and effectively managing these elements are what make network engineers key players in maintaining the Internet's vast and complex landscape. IP addressing assigns unique identifiers to devices on a network, similar to how a home address uniquely identifies a residence for mail delivery. In the digital world, an IP Internet Protocol address ensures data reaches the correct device on a network. EP4 Internet Protocol version 4. Description: EP4 is the fourth version of the Internet Protocol, providing about 4 billion unique addresses. Each address is 32 bits long, displayed as 4 decimal numbers separated by dots, e.g. 192.168.11. IP4 address classes. Class A for large networks, e.g. multinational companies with the first number ranging from 1 to 126. Class B aimed at medium-sized networks, e.g. universities with the first number from 128 to 191. Class C suitable for smaller networks, e.g. small businesses, with the first number between 192 and 223. Class D used for multicast groups, with the first number from 224 to 239. Class E reserved for future or experimental use, ranging from 240 to 255 in the first number. Subnet mask assignment function. Subnet masks define which part of an IP address is the network portion and which part is the host. They help organize a network into smaller groups for more efficient traffic management. Subnetting. Analogy: subnetting is like dividing a large group into smaller groups for efficiency, similar to organizing students in a classroom. Public vs. private networks in IP4. Public IP addresses comparable to a home street address, visible to the world. Private IP addresses like the rooms within a home, known only to those inside. Private address ranges. Usage: set aside for use within private networks, akin to unlisted phone numbers. Classless interdomain routing sitter. Description: sitter is a method for allocating IP addresses and routing. offering more flexibility compared to traditional methods similar to organizing a library by genres. Default gateways. Role. A default gateway acts as the exit door from a local network to the wider internet, functioning as the router's IP address. Virtual IP VIP. Concept. A VIP is an IP address shared among multiple devices, like a pseudonym used by several writers. IP4 address types. Unicast address, used for one-to-one communication, similar to a direct phone call. Broadcast address, for sending a message to everyone on a local network, like a town crier in a market square. Multicast sends messages to a specific group of devices, akin to sending invitations to a select group of friends. This structured overview provides a clear understanding of IP addressing and its various components essential for network configuration and management. Network engineer training. IP addressing is a fundamental aspect of network configuration and communication, assigning unique identifiers to devices on a network to ensure data is routed to the correct destination. Here's a summary of the various aspects of IP addressing. IP addressing overview. IP addresses are like digital addresses for devices on a network, ensuring that data sent over the internet reaches the right destination, much like mail to a home address. They are crucial for identifying devices and routing traffic in networks. IP4 Internet Protocol version 4. IP4 is the fourth iteration of the Internet Protocol, providing approximately 4 billion unique addresses. Each address is 32 bits long, structured as 4 decimal numbers separated by dots. Despite its widespread use, the limited address space of IP4 has led to the eventual need for IP60 to address exhaustion. IP4 address classes. IP4 addresses are categorized into classes based on the network size and requirements. Class A, large networks e.g. multinational corporations. Class B, medium-sized networks e.g. universities. Class C, small networks e.g. small businesses. Class D, multicast groups. Class E, reserved for future or experimental use. Subnet mask assignment and subnetting. Subnet masks are used to differentiate the network portion of an IP address from the host portion, helping to organize and manage network traffic efficiently. Subnetting further divides a larger network into smaller, manageable subnetworks, enhancing routing efficiency and network management. Public VS. Private networks in IP4. Public IP addresses, identifiers visible to the wider internet, similar to a home street address. Private IP addresses, used within private networks, not routable on the global internet, akin to rooms within a home. Private address ranges. Private address ranges are reserved for internal use within private networks, helping to conserve global address space and enhance security. Classless interdomain routing sitter. Sitter is a flexible method for allocating IP addresses and routing, replacing the older class-based system. It allows for more efficient use of the address space and better scalability of networks. Default gateways. A default gateway serves as the access point or exit from a local network to the broader internet. It's typically the address of the router on the local network. Virtual IP VIP. A virtual IP is an address that can be shared among multiple devices or servers, often used for load balancing or fault tolerance purposes. IP4 address types. Unicast address, direct one-to-one communication. Broadcast address, sending messages to every device on a local network. Multicast address, sending messages to a specific group of devices. Understanding IP addressing and its various components is essential for network engineers, IT professionals, and administrators for effective network design, configuration, and management. It enables efficient data routing, network planning, and the implementation of security measures. As the digital world continues to expand, the role of IP addressing in facilitating seamless communication and connectivity across diverse networks remains paramount. IP6 addressing, understanding the new era of Internet Protocol. Where have all the IP4 addresses gone? Discussion. This section explores the depletion of IPv4 addresses due to the Internet's rapid expansion and the subsequent need for IP6, offering a larger pool of unique addresses. Identifying IP6 addresses. Overview: IP6 addresses are significantly longer than IP4 addresses to accommodate the massive growth of Internet-connected devices, akin to expanding phone numbers for more users. Types of IP6 addresses. Description: IP6 introduces various address types, such as global unicast, anycast, and multicast, each serving different communication requirements in a network. Global unicast addresses. Function: similar to standard postal addresses, global unicast addresses in IP6 are used for sending and receiving traffic across the global Internet. Link local addresses. Use: link local addresses facilitate communication within the same network segment or link. They are non-routable beyond their specific segment, ensuring local network security and efficiency. Site local addresses. Analogy: comparable to private addresses in IP4, site local addresses are used within an organization or site. They are unique to a particular site or organization and are not intended for public Internet routing. Neighbor discovery. Role: neighbor discovery in IP6 replaces the ARP protocol from IP4. It assists devices within the same local network in recognizing and communicating with each other, similar to how acquaintances acknowledge each other in a neighborhood. This structured format offers a foundational understanding of IP6 addressing, incorporating relatable analogies to simplify complex technical concepts. It provides insights into the evolution from IP4 to IP6 and the functionalities of different IP6 address types. GPT. Network Engineer Training. IP6 Internet Protocol version 6 is the most recent version of the Internet Protocol IP, the communications protocol that provides an identification and location system for computers on networks and routes traffic across the Internet. Understanding IP6 is crucial due to the exponential growth of the Internet and the depletion of IP4 addresses. Here's a summary of the key elements and the importance of IP6 addressing. Depletion of IP4 addresses. The rapid expansion of the Internet has led to the exhaustion of IP4 addresses. IP4, with its 32-bit addressing, allows for approximately 43 billion unique addresses, a number that seemed ample in the early days of the Internet, but is insufficient in the modern era of ubiquitous Internet-connected devices. The depletion of IP4 addresses has necessitated the shift to IP6, which, with 128-bit address space, significantly expands the number of possible unique addresses.